For many years, researchers held the view that the Big Bang marked the genesis of all things: time, spatial dimensions, and physical substance. However, recent findings from the James Webb Telescope present an alternative narrative. The telescope discovered galaxies that appear excessively ancient and overly evolved to align with our current chronological framework. Should Webb's observations prove accurate, it implies the cosmos could have been in existence well prior to the Big Bang event itself. This particular finding is fundamentally altering our understanding of the universe's origins. Should you be intrigued by the unexplored, please subscribe and accompany us on this expedition as we persist in unraveling the cosmos's enigmas. Upon the James Webb Space Telescope commencing its complete operational phase in mid-2022, astronomers anticipated corroboration rather than contradiction. The objective of the mission appeared uncomplicated: to observe the initial few hundred million years of the universe and witness the genesis of the earliest galaxies as they materialized from obscurity. The unique construction of Webb set it apart from all previous telescopes. Its main mirror, gold-coated and measuring 6.5 meters, is composed of 18 accurately positioned segments and gathers over 6 times the amount of light compared to Hubble. This observatory maintains an orbit 1.5 million kilometers distant from Earth, situated at a point of gravitational equilibrium, referred to as L2. Positioned remotely from the planet's heat and luminosity, its instruments, from that steady vantage point, remain cooled to temperatures below -230 degrees Celsius. This enables them to perceive the subtle infrared radiation emitted by the earliest stars, light which has been elongated due to the universe's expansion. Given that light propagates at a finite velocity, approximately 300,000 kilometers per second, each extra light year of separation signifies an additional year further back in time. An instrument capable of detecting subtle infrared radiation functions essentially as a temporal device. The greater the distance it observes, the earlier the cosmic epoch it brings into view. Through its ability to capture wavelengths imperceptible to human vision, Webb gazes back over 13 billion years into history. It is drawing closer to the era when the initial atoms coalesced to form stars and galaxies. As per the conventional cosmological framework, the cosmos originated approximately 13.8 billion years ago from an exceedingly hot and compact condition, which has continuously expanded and cooled since then. Roughly 380,000 years following that inception, the initial atoms came into being, and the luminous plasma mist dissipated, thereby emitting the cosmic microwave background. This subtle residual radiance remains observable even now. Subsequently, a prolonged period devoid of stars ensued, termed the Cosmic Dark Ages, characterized solely by hydrogen and helium gas permeating through space. Gravitational forces gradually drew matter together until the earliest stars ignited approximately 200 million years after the universe's inception. Aggregations of these stars coalesced into more substantial systems, and within a billion years, a considerable quantity of developed galaxies was anticipated to be present. The most profound images captured by Hubble corroborated that chronological sequence. Conversely, Webb was engineered with the purpose of revealing the absent transitional phases. Its initial data compelled researchers to reevaluate their understanding. Within a celestial region no bigger than a single grain of sand viewed at arm's length, an expanse selected due to its apparent emptiness. The inaugural deep field observation by Webb unveiled thousands of galaxies clustered together, resembling cosmic glowing fragments. While some presented as disorganized blurs characteristic of early formation, others manifested as luminous, dense, and remarkably substantial. The illumination from these objects had journeyed for over 13 billion years, presenting us with a universe merely a few hundred million years subsequent to its commencement. Such a degree of structural complexity ought to have been unattainable so shortly following the initial cosmic expansion. Computer models utilizing the Lambda CDM, Lambda Cold Dark Matter Framework forecast that galaxies of similar dimensions require nearly 1 billion years to develop. A particularly notable instance emerged from a Webb investigation designated as GLASS, which stands for the Grissom Lens Amplified Survey. From its orbital vantage point, it detected a dense celestial arrangement now identified as Glass Z13, whose emitted light commenced its voyage approximately 13.5 billion years in the past. Webb observed this system as it existed roughly 320 million years following the universe's genesis. Despite its early age, it already presented as fully developed and radiant, potentially encompassing billions of stellar bodies. Shortly thereafter, an additional prospective object, Sears 93316, emerged from a distinct observational initiative. Dating back approximately 240 million years after the universe's initial expansion, even if subsequent adjustments refine these figures, the underlying pattern remains undeniable. Galaxies were forming at a rate that challenges current theoretical understanding. To fully grasp the extraordinary nature of this phenomenon, consider the typical process by which galaxies are constructed. This begins with the first generation of massive short-lived stars, known as Population 3. Composed entirely of hydrogen and helium, these stars, upon exploding as supernovae, enriched the surrounding gas with heavier elements. These metallic elements enabled the gas to cool more efficiently, leading to its collapse into new stars and facilitating the growth of the earliest galactic structures. However, these cycles are time-intensive. Each generation must complete its life, perish, and recycle its constituents for the next. Observing chemically enriched, well-organized galaxies when the cosmos was still in its nascent stage implies that multiple stellar generations had already emerged and faded in rapid succession. Webb's near-infrared spectrograph confirmed the presence of oxygen, neon, and even carbon, elements that can only form after numerous stellar lifetimes. This evidence pointed to a universe that achieved complexity considerably earlier than anticipated. Initially, some astronomers questioned whether Webb's observations might be misleading. Could these luminous smudges actually be closer galaxies, their light reddened by dust, thereby creating the illusion of vast distance? Might gravitational lensing, where light is bent and magnified by intervening galaxy clusters, be causing ordinary galaxies to appear extraordinary? Research teams across the globe re-examined the data using independent processing pipelines and calibration methodologies. When the characteristic hydrogen emission lines were precisely measured, several of the observed targets proved unequivocally ancient. Located over 13 billion light-years away, the most distant confirmed system to date lies approximately 33 billion light-years from us in the universe as it is stretched today. This means we observe it as it existed merely 330 million years after the first light of creation. More examples are almost certainly awaiting detection as Webb continues its deeper scans. If galaxies of such considerable mass already existed, then something in our current understanding of cosmic evolution is incomplete. The prevailing model assumes that dark matter, the invisible substance comprising about 85% of all matter, provided the gravitational framework upon which ordinary gas condensed. Perhaps dark matter interacted more robustly or aggregated into dense clumps sooner than expected. Another possibility is that primordial gas clouds cooled and condensed with astonishing efficiency, converting a significant portion of their mass directly into stars. Webb's initial data suggests stellar formation rates up to 100 times greater than those observed in the contemporary Milky Way. This intensity was such that entire galaxies might have briefly flared like fireworks before settling into more quiescent states. Even with these proposed adjustments, the numerical discrepancies persist. Simulations must amplify both the rate of matter collapse and the conversion of gas into stars by factors of 10 or more to accurately reproduce what Webb has observed. The most straightforward interpretation is that cosmic structures developed more rapidly than predicted. The more radical proposition is that our very understanding of the universe's chronological progression may require re-evaluation. Should the initial pace of cosmic expansion have varied even marginally from modern estimations, the correlation between spatial separation and temporal progression would be altered. Nevertheless, even substantial corrections are insufficient to completely bridge the observed gap. A foundational element appears to be absent from our mathematical models of the nascent cosmos. Webb's findings also compress the era of reionization, which was the transformation when ultraviolet radiation from the earliest stars ionized hydrogen atoms, rendering space transparent. Prior to Webb, this phenomenon was believed to unfold between 500 and 900 million years following the universe's inception. However, the observation of brilliant galaxies radiating significantly earlier now implies that the process commenced as early as 250 million years after the initial cosmic expansion. Consequently, a remarkably brief interval existed separating cosmic obscurity from luminosity. The universe's dawn appears to have been less a gradual emergence of light and more an instantaneous burst. The telescope's unparalleled sensitivity uncovered an additional enigma, indications of supermassive black holes already present during these primordial epochs. Certain compact, luminous sources identified by Webb could harbor central black holes with masses millions or even billions of times that of our Sun. The development of such colossal entities within merely a few hundred million years necessitates either an exceptionally rapid accretion of gas or the direct gravitational collapse of vast primordial clouds, mechanisms that push the boundaries of contemporary astrophysics. Deciphering the formation of these ancient behemoths has emerged as a pivotal aim for the Webb telescope. To confirm this developing understanding, astronomers are expanding Webb's deep field initiatives and initiating specific projects, including Cosmos Webb, Jades Deep, and Primer. These investigations will chart vast areas of the heavens, tracking the clustering, merging, and evolution of the earliest galaxies. Concurrently, theoreticians are scrutinizing previous hypotheses concerning dark matter, gas cooling, and the universe's expansion, constructing novel simulations to evaluate every potential scenario in the coming years. The growing collection of Webb's data ought to indicate if these findings represent a statistical anomaly or a significant alteration in our comprehension of the universe's self-assembly from an initial state of disorder. What is definitively known is straightforward yet deeply significant. The nascent universe was not the tranquil, gradually developing domain scientists had previously envisioned. Instead, it was densely populated, radiant, and remarkably energetic nearly from its inception. Galaxies formed earlier, stars ignited sooner, and black holes emerged much earlier than anyone had believed feasible. Each fresh image from the James Webb Space Telescope intensifies the enigma and serves as a reminder that the initial light of creation continues to hold untold secrets. As additional Webb data became available, the emerging pattern grew indisputable. Autonomous research groups, employing initiatives like Jades, verified that the nascent cosmos harbored considerably more massive luminous galaxies than anticipated, even subsequent to re-evaluating a handful that turned out to be nearer than initially believed. Many others persisted as remarkably old. Statistical analyses indicated that colossal galaxies were between 10 and 100 times more prevalent in the early universe than any predictive model had projected. This divergence cannot be disregarded as merely an error in observation. Even when researchers increase the efficiency of star formation in their models, simulations are still unable to replicate that rapid pace of growth. Within their theoretical frameworks, the galaxies continue to be too dim to correspond with Webb's observational findings. Gas clouds would need to undergo collapse with nearly flawless efficiency. This would entail converting the bulk of their mass directly into stars, a feat no known process currently achieves. A number of researchers hypothesize that the solution might reside in dark matter, which constitutes the unseen framework that ordinary matter adheres to. If it had aggregated more quickly or with greater density than predicted, it could have accelerated the gravitational collapse of gas. Even a slight modification in how dark matter interacts with itself or with radiation could yield immense implications for galaxy formation. Numerous novel models are presently undergoing testing, utilizing Webb's preliminary data as a standard. The history of the universe's expansion represents another potential contributing factor. A galaxy's age is deduced from the degree to which its light has been stretched as cosmic space expands. Were that initial expansion not entirely uniform, our calculations for distance and time might be marginally incorrect. A more rapid early expansion would lead galaxies to appear older than their true age. This potential scenario is connected to the Hubble tension, which refers to the persistent discrepancy between expansion rates measured in our local vicinity and those inferred from observations of the early universe. Webb's findings could provide the insights needed to resolve this conflict. Nonetheless, even substantial modifications to the expansion rate are insufficient to entirely resolve the enigma. Some of Webb's observed galaxies are simply too massive for the allotted time, irrespective of how the figures are calibrated. For this reason, astronomers are investigating more unconventional concepts, modified gravitational theories, exotic varieties of dark matter, or novel physical principles governing matter's behavior under extreme conditions. These initiatives do not invalidate the Big Bang, but rather aim to refine our understanding of the events that succeeded it. Webb's imagery also suggests the remarkably early emergence of supermassive black holes. Several compact, intensely luminous sources display light patterns consistent with black holes millions or billions of times the sun's mass. The existing timeline offers minimal opportunity for them to evolve from smaller stellar remnants, thereby suggesting their direct formation from collapsing clouds of primordial gas. This direct collapse model might elucidate the rapid appearance of massive black holes and their role in facilitating galaxy formation around them. Additionally, these nascent galaxies may have played a crucial part in ionization. This refers to the epoch when ultraviolet radiation from the earliest stars stripped electrons from hydrogen atoms, thereby making the universe transparent. Webb's data indicates that this process might have commenced hundreds of millions of years earlier than previously hypothesized. This dramatically curtailed the cosmic dark ages. Taken together, these discoveries portray a universe that organized itself with greater speed and efficiency than any existing model accounts for. The equilibrium among gravity, gas, and radiation must have been distinct, potentially calibrated by conditions we have not yet quantified. The nascent cosmos appears to have been denser, more turbulent, and more active than previously conceived. Webb's spectrographs are now poised to meticulously analyze the light from these galaxies, ascertaining their true composition and motion. If these findings are confirmed, the paradox will endure. The universe constructed its initial complex structures more rapidly than current physics allows. This represents the significant challenge Webb has introduced to cosmology. It has not refuted the Big Bang, but instead revealed that the period immediately succeeding it was more tumultuous, more efficient and complex than anyone had previously conceived. If Webb's revelations continue to withstand rigorous scrutiny, they imply that the early cosmos was considerably more intricate than any theory has thus far envisioned. Its images of luminous, well-structured galaxies densely populating the first few 100 million years of existence defy expectations not only in scale, but also in fundamental principle. They prompt a re-examination of the physics governing how matter, energy, and even time initially organized themselves into the universe we perceive today. A primary and pressing enigma revolves around dark matter, the invisible substance that sculpts the cosmic web. In conventional simulations, it behaves as a cold, passive framework that gradually accumulates normal matter solely through gravitational attraction. However, the galaxies observed by Webb seem to have materialized too rapidly for such a gradual process. Certain physicists are currently investigating theories where dark matter interacts with itself, allowing it to push or impact itself, thereby creating concentrated masses that attract gas much more swiftly. Other researchers prefer the concept of fuzzy dark matter, whose extremely light and wave-like particles merge, generating quantum pressure that subtly modifies the development of structures. A small number even hypothesize that it could have had transient interactions with radiation during the early cosmos, initiating gravitational collapse sooner. Every one of these concepts necessitates modifications to particle physics, and each would render the universe considerably more active than the static model presented in academic texts. The initial state of the universe presents another potential explanation. During the rapid inflationary expansion that stretched space within the universe's initial fractions of a second, infinitesimal quantum ripples expanded to astronomical proportions. Had those fluctuations been more pronounced or less consistent than hypothesized? mass could have converged almost immediately into significant gravitational basins. Recent models of inflation, some influenced by string theory and others by the interplay of quantum fields, forecast precisely such a more uneven, less uniform initial state, thereby making the swift formation of galaxies, observed by Webb, a certainty rather than an oddity. Additionally, primordial black holes are considered, which are hypothetical vestiges of intense density fluctuations, which potentially arose before the initial atoms formed, if merely a small quantity of these black holes appeared. These could have functioned as foundational elements for galaxies, pulling in gas, and prompting a series of star-forming events. The force of gravity would warm the incoming material, yielding radiation of sufficient brilliance for Webb to identify across immense cosmic distances. Fascinatingly, a number of the dense, extremely bright objects in Webb's deep field observations reveal the precise spectral characteristics predicted for these particular objects, discovering an unmistakable sign, perhaps a particular X-ray luminescence, or a pattern of gravitational waves would constitute one of the deepest revelations within cosmology, establishing a link between the cosmos's initial state and the enormous formations visible in the present era. Webb's spectroscopic analysis is additionally revealing fresh perspectives on the initial chemical composition of the cosmos. Within galaxies that are under 500 million years old, scientists are already discovering the spectroscopic traces. These include oxygen, nitrogen, magnesium, and even indications of silicon. The presence of such elements is only possible subsequent to numerous generations of colossal stars having completed their existence. Consequently, the initial stellar formations must have emerged with remarkable swiftness, potentially within a mere 100 million years following the universe's inception, as certain simulations suggest. These models propose that the very first stars were incredibly massive, possessing hundreds of times the solar mass. They burned intensely, subsequently collapsing into black holes in a span of merely a few million years. The resulting explosions would have inundated adjacent gas clouds with heavier elements. This facilitated the formation of the subsequent stellar generation with astonishing rapidity. Alternative theories picture intense fusions occurring between developing galaxies. In these events, converging clouds compressed gas, thereby sparking powerful bursts of star formation. Both possibilities portray the nascent cosmos as an environment characterized by disorder and simultaneous creation resembling a cosmic forge more than a tranquil beginning. Of comparable transformative impact is the evidence from Webb suggesting a profound connection between galaxies and supermassive black holes. Within the contemporary universe, black holes expand within the cores of established galaxies. This process unfolds over eons, yet Webb is demonstrating that this association could have commenced considerably earlier, with certain nascent galaxies already housing central black holes. These are millions or billions of times the mass of our Sun, and the emitted radiation from these energetic cores might have agitated, compacted, and governed the adjacent gas, affecting the formation of stars within this cyclical process. Galaxies and their core black holes undergo coevolution, forming a close association, which could have molded the entirety of the universe's structure. These indications propagate outwards. Our comprehension of dark energy, the enigmatic force driving the acceleration of cosmic expansion, is being challenged. Should structures have emerged sooner and more rapidly than anticipated, the interplay between gravitational pull and expansion might have differed historically. Certain cosmologists hypothesize that the potency of dark energy has fluctuated across epochs, commencing feebly and intensifying solely once the cosmos attained a particular age. Conversely, some theorize that the spatial geometry itself might lack perfect uniformity. Such a slight bending could modify our calculations of distances and the fabric of space-time. Current observational projects mapping the distribution of galaxies across various cosmic eras might ascertain if dark energy maintains a constant nature or represents a dynamic process. Furthermore, the most profound inquiry persists: what was the nature of time during the universe's initial moments, close to its genesis? The established principles of physics converge into a realm where quantum theory and gravitation operate concurrently. Certain theoreticians put forth the idea that time itself became more substantial as the cosmos expanded, exhibiting a different flow in its nascent stages compared to its present state. Given those circumstances, what we perceive as 300 million years might have elapsed in only a fraction of that period, as per the universe's intrinsic temporal rhythm. Other researchers advance the hypothesis that our cosmos could have originated from a prior universe through a rebound event. From this perspective, a preceding cosmos underwent gravitational collapse, was compacted into a state of ultimate density, and subsequently rebounded, leaving behind subtle vestiges. These patterns of density ultimately form the cosmic web of galaxies that is currently observed. Should any indication of such a preceding cosmic cycle be discernible within Webb's observational data, it would fundamentally alter our conception of the universe's genesis itself for the exploration of these uncharted territories. Astronomers are devising a completely novel suite of analytical instruments. Highly advanced algorithms currently track each individual photon registered by Webb. By reconstructing the trajectory of light through the expanding cosmos, to deduce the evolutionary pathways of galaxies, both chemically and dynamically. Furthermore, machine learning platforms are contrasting numerous simulated cosmic models against authentic observational data, seeking to identify which fundamental physical principles most accurately replicate the phenomena observed by Webb. From a theoretical standpoint, cosmologists are integrating the mathematical frameworks of quantum gravity, alongside extensive simulations in an endeavor to span the divide, separating the most minute particles from the most colossal cosmic formations. Additional observatories are contributing to this endeavor, including radio telescopes like LOFAR in Europe, and the forthcoming square-kilometer array in Australia is set to chart the subtle 21-centimeter signal from neutral hydrogen, illustrating the dissipation of the cosmic fog during reionization. In the United States, the CMBS-4 experiment is slated to reevaluate the primordial microwave background, with unparalleled accuracy, assessing if minute discrepancies align with the galactic web. Even gravitational wave observatories, such as LISA, slated for the 2030s, could potentially detect the ambient resonance of primordial black holes, or initial mergers that contributed to forming the earliest galaxies. Every new device contributes a further element to the enigma. While Webb might have ignited the initial insight, these observatories collectively have the potential to elucidate the entire causal sequence from the universe's inception to the immense formations we currently occupy progressively. These efforts will ascertain if the universe genuinely progressed more rapidly than theoretical models permit, or if we are, in fact, perceiving a more profound stratum of physics intrinsically integrated into the very essence of reality. Irrespective of the ultimate conclusions, one truth is already undeniably established. The nascent universe was remarkably vibrant. It exhibited both turbulence and order. Disordered yet inventive, a domain where gravitation, radiation, and matter collaborated to construct intricacy. In a remarkably short span, the James Webb Space Telescope has not simply broadened our perspective into antiquity, it has unveiled an entrance to a domain where the accustomed principles of nature start to become indistinct, serving as a reminder that the narrative of creation is continually being composed photon by photon by the James Webb Space Telescope. It has not only broadened our understanding of space, but also fundamentally altered our perception of time. Within merely a few years, it has demonstrated that the nascent cosmos was not a tranquil cradle, but rather a tempest of genesis, where matter, light, and gravitational forces interacted in remarkable synchronicity. Every fresh revelation pushes the limits of what we previously believed achievable, compelling scientific fields to revise their most ancient narratives. Currently, the effort to decipher Webb's findings is underway. Its data repository, already containing petabytes of information, has evolved into a valuable guide. For both cosmologists and physicists, novel algorithms are being developed to interpret this chart, seeking out configurations concealed from human vision, such as faint galaxies obscured by background interference. Unusual chromatic indicators suggesting undiscovered chemical compositions, as well as spatial warps that could indicate the existence of unseen material. AI has started to locate celestial bodies so dim that they push the very boundaries of what the Webb telescope itself is capable of discerning, implying that the nascent universe could be even more active than our current observational tools are presently able to verify. The subsequent wave of space observation platforms is getting ready to assume responsibility. The Nancy Grace Roman Space Telescope, scheduled for deployment later in this decade, is set to survey extensive areas of the heavens to quantify cosmic architecture on an immense scope. The Habitable Worlds Observatory, which remains in its conceptual design stage, is poised to broaden Webb's enduring impact from galaxies to exoplanets, investigating celestial bodies orbiting remote stars, in pursuit of chemical indicators of biological activity. Looking further into the future, mission strategists foresee observatories that are either chilled by liquid helium or shielded by light-blocking structures spanning a kilometer, sails that can intercept and gather even longer wavelengths. As Webb gazes outward at the earliest molecular clouds, physicists are simultaneously exploring the universe's inner mechanisms towards the universe's concealed framework with subterranean experiments, like Lux Zeppelin located in South Dakota and Xenon situated in Italy, are actively searching for the difficult-to-detect particles that could compose dark matter. Projects like DSI and Euclid, among others, are charting the current movement patterns of galaxies, probing whether the fundamental rules of gravity could themselves change over the vast stretches of cosmic time. Combined, these initiatives create a connection between the universe's most expansive and most microscopic scales, merging astrophysics with particle physics in the pursuit of one coherent vision of reality. Nevertheless, the Webb telescope's influence extends beyond mere laboratories and calculations. It has rekindled a query as ancient as humankind. What is the origin of all structure? If the cosmos arranged itself so quickly, perhaps the act of creation is not uncommon. Perhaps this is the universe's inherent behavior. Certain researchers are investigating the concept of cosmic self-organization, where intricate patterns emerge without external intervention whenever energy traverses matter. Be it within galaxies, atmospheric disturbances, or biological cells, the foundational principles that sculpted the earliest stars might still resonate within life's chemical processes and the genesis of human cognition. Every photon Webb records represents a faint echo from an era predating the existence of vision or conscious thought. These subtle signals journeyed for billions of years to arrive here, bearing recollections of a universe that was nascent, scorching, and abundant with potential. When we analyze them, we are not merely observing ancient galactic formations. We are deciphering the prelude to our very own being. With Webb's mission ongoing, humankind finds itself on the threshold of an innovative scientific discipline, one that integrates direct observation, computational modeling, and creative thought. Subsequent telescopes will venture even deeper, potentially uncovering the shift from absolute void to tangible existence. The instant the cosmos initially acquired the ability to generate. Until that time, each fresh image transmitted by Webb serves as a reminder that the void separating stars is not barrenness, but rather a chronicle awaiting interpretation. While the telescope's reflective surface is positioned far from our planet, what it reveals is profoundly human. Our inquisitiveness, our tenacity, and our profound desire to ascertain the true genesis of all things. Should you have found this exploration into the universe's initial illumination enjoyable, please remember to give a like and subscribe. This assists in bringing this journey of discovery to a wider audience of inquisitive individuals. We appreciate you watching. The narrative of the universe continues to develop, and collectively, we are merely commencing the reading of its subsequent chapter.